Dear colleagues, let me open the plenary session. The session is chaired by Professor Platonov and by me, Professor Igorov. So, Alexey Viktorovich, please.
Morning, my colleagues. Now we have one plenary report, Professor Sorina Laru, from control invariant sets to an inverse optimal perspective on the constrained control design. Professor, if you are ready, begin please.
Yes, thank you. Okay, I will share my screen. Well, sorry, I don't know if you see. Okay. So, do you see the screen? Everything
Yes,
is
I do.
okay. Good. Good morning, everyone, and thank you for being here. Thank you for the invitation. Thank you to the organizer for the great job that they are doing for organizing this event in the memory of Professor Vladimir Zubov. I will talk today about control invariant sets, and this is related with the work of Professor Zubov by the interest that he dedicated to the characterization of domains of attraction of different dynamical systems. And in particular, I will look at these concepts as they are used in the modern control design in the presence of constraints, and the optimization-based design will be one of the key concepts. So the agenda of the day, I'll come back on the definitions, some very basic notions about set invariance and constraint control, and then I will dwell for some time on two classical control methodologies, namely vertex control and then model predictive control. And maybe the most of the time I'll spend on the interpolation-based control, which bridges a gap in between those two classical design methodologies. I will end up with some philosophical notions that may broaden the area and the view on this constraint control design. Okay, so let's come back on some very basic and classical notions. So all my talk will be related with the sets defined in a finite dimensional space, so which is represents in the same time the state space of a dynamical system. And I will be interested on the way that those sets behave in relationship with a dynamical system, let it be discrete time or continuous time. And we'll call this static object, the set X, positive invariant with respect to the dynamical system if for any initial condition within the set, the solutions, so the future trajectories will lie within the set itself at any future time instant. I put here an operator that can be continuous time differentiation or difference operator if we are in discrete time. Now, the notion is well understood, and for continuous time, practically by the continuity of the solutions, practically we have to look at the frontier of this domain and check the vector field and make sure that this vector field is within the tangent cone which points inside the set that we want to analyze. Now, if we are in discrete time, the story is a little bit more complicated. Looking only at the frontiers of those sets is not enough. So whenever this operator here is a difference operator, then the positive invariance of a set cannot be judged only in particular case can be judged on the frontier, but in the general case of nonlinear maps, have to be checked by the inclusion of the forward map within the set itself. So this is a very basic definition, a basic notion understood from in mathematics from the 30s, 40s, used in control then in different works. And then in the 70s and 80s, there was an interest for the construction of those sets. How do we construct, at least in some particular classes of system, and what can be simpler than the linear time invariant framework? So let's look for 1 second what happens with a dynamical system, a linear dynamical system in Rn, for which we have an output selection, and this output is constrained to be within a polytopic set. Well, the question is, which is the largest invariant set within this domain, admissible domain Y? And this set will be denoted like maximal admissible set, and its definition will be the collection of all the points such that the future trajectories passed by the output equation lie within the set itself. So can this set, which is an infinite practically, if we try to add here all the possible inequalities coming from the definition of the set at all future instants, obviously we got an infinite number of constraints. So this infinite characterized set, it can be practically constructed. Is it finite in some framework? And interestingly, only in the 90s we have a strong result on the construction of the maximal output admissible set, which builds on the set iteration and constructs, instead of the infinite set in here, construct iterative sets. So the collection of initial points that stay within the output set or satisfy the state space constraints for a finite number of steps. And then, of course, we can iteratively increase the indexing here and construct sets that guarantee the satisfaction of constraints for longer and longer horizons. And we have a strong theorem in here saying that if the operator A is asymptotically stable, so in discrete times the matrix is sure, and the pair CA is observable, it's if Y is bounded, the set that we are trying to analyze with respect to the constraints is bounded, obviously the fixed point has to be inside this set, then the set that we are trying to characterize is finitely determined. So we see from this result that we have a direct relationship in between the asymptotic stability, observability, and then some well-posedness conditions on the topology of the set. Now, this result says only that there is some finite index where those iterations will stop. So even if in abstract manner, the maximal set in there has an infinite number of constraints, its definition will stop at some point with a finite representation in terms of polytopes, for example, in the case that I described here. But it's nothing said here about the complexity of this set. Would it be a simple set, as simple as the set of constraints? Is n here so large that we cannot even store this set? And the links between the eigenstructure of the linear operator defining the dynamical system and the complexity of the invariant set has been studied in some classical works coming from the Russian school with Molchanov, Bobileva, and Piatnitsky. And I will add to this broad picture and basic definition some rings of set invariance with stability. If somebody provides me, I'm not trying anymore to construct the invariant set. Somebody comes, an oracle, and gives me a polyhedral set, and I have to certify if this set in there is positive invariant with respect to, again, let's take a simple dynamic in here. Well, in the 80s, there was a very elegant result showing that such property can be certified by the existence of a matrix H with non-negative elements, and these non-negative elements the non-negative property of the elements of H is very important, satisfying some simple linear inequalities. I'll not enter into the proof of these results, but I will only stress that the constraints here are linear. So practically the certification passed by a very simple resolution of a linear program. In the same time, another important aspect is that the non-negativity of the elements of the matrix H relates the constraint system, the constraint linear dynamic, to a positive dynamical system of dimension where R is here obviously different of N. So we have positive invariance if there exists a sort of comparison system which respects the same stability properties, but has on top of that some positivity characteristics. Going further, for any invariant set, which is endorsed with some contractiveness properties, we can use the respective invariant set as polyhedral Lyapunov candidate, and this proved to be a very versatile tool in the analysis of different class of dynamical system like hybrid system, switch system, linear parameter varying system, and so on. Okay, in the few slides that I showed till now, the system was autonomous. Well, what happens is the system that we are dealing with is to be controlled. So we can choose the input U in order to enhance the positivity properties. For example, if the system is not stable, U will have the main objective of stabilizing the system. And then additionally, we can look further and try to enlarge the positive invariant set related to the closed loop functioning. So the definition is simple. So now any initial condition in the set have to have an associated control law, and this control law will drive the future any future time step, the trajectories within the set, not violating the constraints. Again, the same question: can we construct these sets? And the answer, at least in the linear case, is positive. Yes, for discrete time linear system, for example, we can pass by the Minkowski addition of the different bounded set in the assumptions, like the state constraints, the input constraints, and we can construct a sequence of sets. And these sets approach the maximal control invariant this time set. Unfortunately, there is no strong result as in the case of autonomous system. So here we can only approach asymptotically the maximal control invariant set. However, we can have epsilon approximation, so we can go as close as we want from this maximal invariant set. So, well, if we having these tools in our backpack, we can look at different ways than the control engineers design feedback control in order to satisfy constraints and enlarge the domain of actions. So historical, by now has more than 30 years control strategy is the so-called vertex control established by Perl Hotman and his collaborator Fichel in '86. At that time, the parlance, the nomenclature was not talking about control invariance. But if you look at the conditions that are established in there, they said that necessary and sufficient condition for the stabilization of LTI system with polyhedral state and control constraints is to have at each vertex of the feasible set that we are trying to characterize at least one control U that brings the state to the interior of the set. But that it's exactly the definition of control invariance. So practically, they link the control design, the constraint control design, to the existence of a control invariant set. More than that, the result, they propose a practical way to combine those extreme actions at the vertices of the feasible domain. So at each vertex in here, there is a vector field or one-step control action, which push the trajectories within the set. And based on the control action on each of those vertices, we can split the feasible domain in simplices, and each of those simplices, we can use convex combination of the control actions on the extreme points. So that is the essence of the vertex control. Just use convex combination with respect to the extreme actions on the control on the boundary of the set of the control invariant set, and then we have a closed loop system. It's one of the first methodologies that starts from sets and build control action satisfying the constraint and ensuring the closed loop stability. Of course, as we have a control invariant set, this is related to the existence of a polyhedral Lyapunov function, and by the fact that we are practically shrinking the Lyapunov function, we have a homotopy in between the feasible set when we construct the Lyapunov function level curves. Okay. That was the vertex control. Very simple approach. Once we design a control, we have a control invariant set with only the control action on the boundary. We can fulfill completely the control definition in the interior. But that doesn't come with any performance whatsoever. And we know from the optimal control theory that we can design elegant and mathematically sound theory starting from optimal control framework. The problem with the optimal control framework in conjunction with the constraints, with the existence of states on input constraints, that it becomes intractable. So the control action in there cannot be solved with an optimization in real time. So of course there are cases when we can find a bang type of policies, but those cases are rather particular. And then in the 80s and 90s, the so-called model predictive control came with a framework for the design of constraint control based on that optimality. So there is an optimization of a cost function which runs on a finite horizon from the current step in the system evolution to k plus n. So that will be the prediction window, to which we add a final term, a penalty on the final term, and then by adding the state evolution constraints and all the static constraints that we may have from the state and input constraints, and adding, very important here, a terminal constraint. Generally, the terminal constraint in here, so the constraint on the arrival state at the end of the prediction horizon. So this constraint in here is designed in conjunction with the terminal cost in order to achieve stability. If those terms in here, the one in the cost and the terminal constraint, don't exist, then practically the guarantees of stability of such a optimal finite time optimal control policy is not guaranteed. And I stress this point in here because it makes a link with what I presented at the beginning. Practically the setting here has to be control invariant in order to achieve the closed loop stability of the MPC controller. And this has been theoretically described in the beginning of the year 2000 in a review paper by David Main and his co-authors, which says practically that our design of an MPC controller will be proper from the stability point of view if at the end of the prediction horizon, for any point in the terminal set, there is a control action which let us continue within the set. So this is nothing else than the definition of control positive invariance that I gave at the beginning. And then if the terminal cost plays the role of a local Lyapunov function. So practically we are free to optimize on a finite horizon as long as at the end of this prediction horizon, we land in a safe set, which is endowed with a local control Lyapunov function. So this is probably the most popular and theoretically sound formulation of constraint control methodology, the model predictive control. And that's excellent. We have a powerful tool, but this tool in here comes with a high computational load, because the performance of this controller, as for the optimal control, the infinite time optimal control, will be the key point in here will be the length, the size of the prediction horizon. So whenever the control horizon, the prediction horizon is long, the computational time will be huge. And if we compare these two classical control methodologies, the vertex control and the MPC, we can find already a comparison which tells us what we can expect. The vertex controller, let's take a very simple double integrator here. So that will be the feasible domain, if you want the control, maximal controllable control invariant set. And if I start on one of the vertex, with the vertex controller, the control action, if you look at the control action in here, the control action is not exploiting the full freedom, the full degrees of freedom in the control. So it's not saturating the control in here. Practically, once I enter within the set, I work with a scaled version of this control inputs. So practically, this use, non-optimal use of the input energy lead us to a trajectory which is rather slow, and we see that the convergence time for the vertex control is much longer than for MPC control. So MPC controller wins the performance competition. It's obviously the best thing that we can think of if we want to optimize the performances. However, the vertex controller is extremely simple. It doesn't play with horizon, it doesn't have terminal constraints. It's only a simple interpolation, convex combination of control action on the boundaries. So if you want low complexity control, then opt for the vertex controller, and the MPC controller will be the one with high performances at a high cost. But in between these two extremes, for a long time, there was nothing to bridge the gap. If I want to be not that performant, but to be a little bit faster, what is to be done in there? And then in the years 2000, there is a research attention dedicated to how to speed up the MPC implementation. And we reached the era of the so-called explicit MPC, where the Karush-Kuntako optimality condition have been used in order to express this optimization phenomenon, which is solved at each moment in time, and practically exploit the active sets and the optimality condition in order to devise explicit formulation. So it has been shown that practically the feasible set in here can be partitioned in a polyhedral, in a union of polyhedral sets, and within each such polyhedral set, we can define the optimal control action in terms of an affine state feedback. And for example, again, for the double integrator that we saw before, for this type of simulation in here, practically the control action is given. Here is the LQ controller, the unconstrained controller. Then you have the saturations, high bound and lower bound. And then there are regions where there is a mix of those fine mappings, all by guaranteeing the continuity of the feedback controller. Now, this is interesting once from the structural point of view, and then we move part of the computational load offline. We are not optimizing anymore online. We do the hard work offline, and then online we come and we position ourselves. For example, if the state is in this red piece in here, then a set of inequalities is verified. And then for this setting here, I look in a lookup table and I can evaluate the control action with a very simple multiplication addition type of operations. So this speeds up the online implementation, but it doesn't solve completely the computational issue, because this partitioning here can be extremely complex. That is where the interpolation-based control came into place. And simply, I will define in one slide the philosophy with drawing. It's always simpler with a drawing. So suppose that we have, as in the MPC or in the vertex controller, you have an approximation of the maximal control invariant set. So that will be the red region in here. And we discussed also about the maximal output admissible set. Suppose that you have an LQ controller, the one that you prefer, that has the best performances in the unconstrained case. And you can, for that specific controller, you can construct a control invariant set with a linear feedback. So we have two sets. And this, if you want, is exactly what we see in the MPC controller. That's the setting here, I can build it offline and very fast. And the feasible set, we have it also. So if it's something complex in here, it's not the definition of the inner set of the outer set. The complexity comes from the filling in of the puzzle with all these pieces in here. So what we can do, if we have only the outer set and the inner set, if we want to avoid high computational load, given a state that's some current time step, we have the current state, then we can look for a pair of points, one XO, which is in the inner set, the control invariant set with the high performances, and XV will be a point in the outer set. And if this pair of points describe my current state in terms of a convex combination like that, then the associated control law, which interpolates with the same coefficients in here, the control action in the 2 points in here, might have very interesting properties. Okay, you can say, well, okay, we have linearity, convexity of those sets. So yeah, I can see that, for example, that the trajectories will stay in there. What about the convergence of such a policy? Well, then we have this theorem in here saying that the control law, any control law obtained by such an interpolation is recursively feasible, so that we already discussed. More than that, if we try to find the C scalar interpolation factor, which has a minimization, practically, we try to find those points in here in such a way that the segment x0 with respect to the ratio of the full segment is the smallest possible, then we have the interpolation factor, which plays the role of a non-increasing Lyapunov function. So practically, if we optimize the C interpolation factor in real time, we move from the outer set towards the inner set with a change of topology in the Lyapunov function at the price of a very simple linear programming with no prediction horizon, with no performance indexes or terminal constraints, only by interpolating in between two control Lyapunov functions. And let's look closer to what's this optimization. Okay, I already unveiled the computational property, which are LP, but if we write the optimization of this interpolation coefficient, it doesn't appear straightforward, the linearity. So the problem is that the following: we try to minimize the interpolation coefficient, or by finding the pair of points for which this interpolation coefficient is the minimum. So we want one of the sets of the points in the convex combination to be in the outer set, the other in an inner set. This is linear up to here, but in this constraint in here, this equality constraint, we have bilinearity. So it's something nonlinear because C multiplies XV, and here C will multiply XO. So this is nonlinear. However, we show that with a change of coordinates, we can rephrase this optimization problem in the form of a linear programming. So practically the minimization of the interpolation factor really comes at the price of linear programming. Very low complexity. What about the performances? Well, you recall vertex control was very simple, but it was not very performant. Well, with the interpolation control, we bridge this gap. We have the MPC type of control action for a double integrator, and practically with a very simple interpolation based on inner programming, we obtain practically a control action which is very similar, and the trajectories in the state space are extremely performant. That would be in the phase plane, the MPC closed loop, and the interpolation-based controller. So this proves visually that the interpolation-based control provides this gap in between, bridge this gap in between the vertex control and MPC performances, all by having a low complexity. Let me show you that this is not only geometry and mathematics. This has a real-world application. So one of my PhD students, François, is working with Renault on the motion queuing design. So this application, you have the test cars that are in a virtual reality, that they are placed on the moving platform, hexapod, that can have longitudinal, lateral moves at a very high accelerations, and they can tilt also and move. And the idea will be to offer to the driver practically real world sensation of driving. The problem is that this platform has obviously limited size in both X and Y direction, and we have also constraints from the acceleration point of view. So how to design this closed loop in order to provide to the cabin, to the driver, the acceleration that it would have had in real time on a driving car. So we know practically the virtual, what the virtual vehicle has to do, but we have a platform which is constrained, and we have to render an acceleration which is as close as possible in the limit of our constraint manipulation. And we can act on the rails, on the hexapod, we can use the sensor, and this is done obviously very naturally in a constraint MPC, where we take the acceleration, we feedback with constraint optimization and close the loop. Unfortunately, the computation time has to be very, very low, less than a millisecond, in order to be able to control this mechanical system. So what we've done, we implemented the control algorithm based on the interpolation based, where we knew a priori which are the high performance invariant set and the outer practically maximal domain of constraint control operation, and then we mix them in an interpolation-based control, as you saw previously, in order to operate the system. There is a supplementary element here. You need a reference governor, because all the presentation that I've done before was about regulation at the origin. Now we want to track some referencing here, and those sets are not centered in this reference. So you have to add an additional level of reference governor, where you find the closest recentering of your set according to the topology of the invariant set. So that would be, if I'm in this state here, I cannot go to the red set, but I can go to the X tilde in here, which is a new reference. So I'll start moving to this one in here, and as I'm moving towards this position, then I can scale the invariant set and then shift them, and in this way advance towards the real reference that I'm willing to track. So we have the low complexity interpolation based, and then this reference tracking strategy. And I compare here what a model predictive control will do. So this is the domain of operation with position and speed. And the predictive control is rather cautious by the fact that it looks on ahead on the prediction horizon. It sees the possible intersection with the boundaries of the domain, of the feasible domain, and stays far from that domain, while the interpolation based control exploits maximally the feasible domain. And you can see here, for example, that would be an ideal car running on the circuit. And as we are running in a virtual environment, we have saturations from the hexapod and the control actions, and then practically the MPC and the IBT, the blue and the red, are very close to one to the other, but the IBT provides higher acceleration, better acceleration than the MPC. Okay, 5-10 minutes to go a little bit beyond this rather structure and computational aspect. We may wonder the explicit MPC about the structure of this interpolation-based control. We saw that the MPC has a piecewise affine structure, and we can have explicit solutions. So the question is, will that be the case also for the interpolation-based control? And in fact, the interpolation-based control is nothing else that, as I was saying, is the we find n+1 points in there, and then based on this coefficient of this interpolation, we mix the control action on the extreme points. It's a little bit like in the vertex control, only that we are not playing only with the outer set, but with two sets in this interpolation. And it can be shown that we preserve practically the same structure, the same piecewise affine structure over a polyhedral partition of the state space. So if we compare the explicit MPC with very complicated explicit solution using the interpolation-based control and the explicit formulation, we can go practically with 1 order of magnitude lower in the complexity. And that would be, for example, an MPC controller in explicit form, and that would be the interpolation-based control, again, 10 times lower complexity. And seeing this kind of result, what we can ask ourselves philosophically, okay, we saw the MPC is very performant. With the interpolation-based control, practically we get the same performance at a lower complexity, but is there any other even lower complexity? What is the lowest possible optimization-based control which offers the same domain of attraction, the same control invariant set? So this turns to be a very complicated problem, and it's related with the inverse optimality, because we try to construct an optimal control problem that will have as a solution a certain domain, and maybe also a given structure if we have a priori piecewise affine characterization, for example, coming from MPC. And we try to solve this problem, and in a nutshell, the problem that we try to address is the following. Given polyhedral partition, that is your best piecewise affine controller, that's the control action that we want to obtain, to replicate by an optimization problem. We try to find a convex cost function equivalent with the optimal control cost function, and the set of convex constraints. The convexity obviously comes in there in order to have a friendly optimization problem, such that the result of this optimization to be exactly the ideal control action that we would like to implement. So in order to solve this problem, we have to pass by the concept of piecewise affine lifting. Why? Because we have this partition in there, and the partition in itself doesn't give us the full information on the topology. So only by storing such a collection of complex sets, we don't have the complexity of the of different subsets or different unions. So I'll call it convex piecewise affine lifting a function that goes in a higher dimension, right? So I'm looking for a function which is continuous, and the epigraph of this function is convex, in such a way that practically the faces of the function z of x project in the partition itself. Many words don't make from the understanding point of view um, the weight of illustration. So I use here a very simple illustration. Suppose that you are in 2D and you have this puzzle down there with the regions blue, green, and yellow. When what I'm looking for is a function in the third dimension such that the function, the faces of this polyhedral set project themselves exactly on the pieces on the two-dimensional original partition. So the question is, can this be constructed in a rigorous manner, in a computational tractable way? And the answer is somewhere at the end of the 19th century with the work of Georgi Fedosevich Voronoi, which was looking at this type of constructions where we try to partition a given region in the state space with regions where all the points are equally distant from the neighbors. And he showed that practically this type of construction relates with a convex function, with the projection of the convex function from a higher dimensional space. So practically you have the conditions for the existence of such a convex liftable function. So in my design, in my few slides that I have to show you next, I start from the assumption that this condition related to the Voronoi work. So my partition is convexly liftable, and the set itself, my control invariant set, is a partition of a polytope. So it's a polytope in itself. So if this holds, let us illustrate this. So let's have a partition in one dimension. So we are on one dimension, on one line here, and we have different segments in here. And this is the function that I want to replicate, that I want to obtain as a solution of a convex optimization problem. How to do that? So first, I take the partitions, so only these intervals in here. I forget about my function. I concentrate on the union of this interval, and I'm constructing a piecewise affine function, which is convex. You agree with me that the function in here, defined over this domain in here, is indeed convex, and its projection, so the projection of the blue segment in here is the blue segment on the line, and so on and so forth. So now, starting from this lifting, I can work and move the vertices in here according to the coordinates of the piecewise affine function that I want to replicate. So while moving those vertices in here, I create a 3D function. And by taking then the convex whole, I obtain a feasible domain. And that feasible domain is convex and can be used by an optimization problem in order to position always on the lower point in this convex domain. And this is practically the essence of a geometrical construction of an optimization problem that solves the inverse optimality problem from any piecewise affine controller, for any constraint controller. And two implications, two theorems. One theorem which says that any continuous piecewise affine function defined over a polyhedral partition can be obtained by parametric linear quadratic programming with only one supplementary variable. So the prediction horizon, if you want, in MPC, and this is the result in the same in the corollary, is that whatever is the MPC design that you are doing, there is another MPC problem which has practically the same performances and only two prediction steps. So this is the lowest complexity that you can ever achieve. And a simple illustration, starting with a double integrator, constraint on the input, on the output. Let's take not too high or prediction horizon of 5 steps. You have this explicit solution in here. And if you work with the inverse optimality, then instead of working in dimension 5, you'll optimize only in dimension 2, which is obviously a huge difference. And the number of constraints in here, well, you have 1, 2, 3 times the addition horizon unit is 5, so 15, and plus the constraints coming from the terminal constraints. So there are about 20 constraints in here, while the inverse optimality based controller has 24. So practically the same complexity in constraints terms, but instead of working in dimension 5, we are optimizing in dimension 2. So that will be the end of my talk. I wanted to stress that invariant sets play a crucial role in the constraint control design. It can be found in MPC, in vertex control, interpolation. All those techniques use it. And then if we go to the structure of the controller, often in linear, for linear system, it's a piecewise control, meaning that the closed loop is a hybrid system. And it's rather computationally expensive to construct explicit solution in higher dimension. However, it gives a lot of insight on the structure. And if we want to understand what's the limit in the complexity in there, we have to go by inverse optimality, convex lifting, in order to understand what can be done. This was what I wanted to convey to you this morning. And I'm open for questions.
Thank you, Professor Alaro. Are there any questions?
I have one question. Professor, could you show the slide 16?
Yes. Yes.
Oh, maybe 17. With the algorithm, with the LP problem.
Yeah. Okay.
Thank you. So, I see. So the feasible set, I mean the big set on your pictures, is polytopic.
Yes. The one in here, so the big one that we have in here, the outer set is polytopic, and practically it's playing a role in the choice of one of the interpolation points in here.
Of course, you should be inside this feasible.
Yes, we have to have this point in here have to be in the red set. The other has to be inside a small set. And now, those are the two constraints. And now I wanted my current state to be on the line which unites these 2 points.
Sure, I see. Yeah, it was my question. Yeah, how do you take into account the fact that XV is inside this feasible set?
Yes. Yeah.
And another question, maybe it's a naive question about invariant sets. Are they robust with some perturbations?
Well, that was a dilemma that I had when presenting the material. So I choose to present here only the results without disturbance. But all the definition, if you see here, the original definition says that the set is invariant if there is a U. Now, there are two signals in here, the control and the disturbance signal. So the solution satisfies the constraints, but then is somehow hidden in here. What are the other, those exogenous signal doing? So this one is my control. So I show that practically our work is to design this for the positive invariance, while this one, it plays against us. And that will be the robust positive invariant counterpart of all those concepts. So that's why in here, for example, I illustrated a cone of possible direction, because if I choose my control, if I am in this position in here, according to the disturbances, I can go in several directions, and that will be the robust version of the positive invariance. And practically all the notions that I presented here up to the inverse optimality hold also for the robust version, but it will be much more complicated to present them.
Thank you very much.
More questions? Professor, do you use constraints on control only in form of linear inequalities or in arbitrary convex form?
Okay, yeah. Well, I have to say that of course, we can have, for example, quadratic constraints, for example, on the energy of the input. And I saw yesterday some nice presentation. Well, in MPC, for example, that will lead us in here. For example, we have a quadratic cost. Well, we have the dynamics. If the system is linear, that will be linear. Well, if we have quadratic constraints in here, the optimization problem will be quadratic programming with quadratic constraints, which is rather more complicated from the computational point of view than the classical QP, which acts with active sets and so on. So we work also with quadratic constraints, but then the optimization algorithms are even more complex than the one in here, which suffers from this optimization problem. So if you have quadratic constraint, what I advise is to approximate that with linear constraints, with inner polyhedral constraints, and then implement. So my experience with even with convex constraints, so quadratic constraints, whenever the constraints get quadratic in the formulation in here, the computational load is rather high.
Thank you very much. Так, more questions? Once again, thank to Professor Olaro for the presentation.
Thank you. Thank you very much. And, thanks again for the invitation. It was a real pleasure. Well, I would like to see the autumn in St. Petersburg, but we have unfortunately to wait a little bit for this pandemic to pass by. So good luck with the organization, and looking forward for the next days of the conference.
Thank you for your participation. Indeed, this year is nice.
Yes. Well,
okay.
Thank you. Thank you.
Thank you. Goodbye.
Goodbye.
Thank you.
Goodbye, colleagues.